Imagine a piece of another world crossing the darkness between stars for millions of years, only to race through our solar system before disappearing back into interstellar space. These objects are more than strange visitors. They are physical fragments from planetary systems we may never be able to reach, carrying clues about environments that formed around completely different stars. The first challenge is figuring out where they came from. Astronomers can use high-precision orbital mechanics to reconstruct an interstellar object's trajectory. By carefully measuring its position and velocity, researchers can calculate its exit vector and mathematically trace its path backward through the galaxy. The farther back we follow that trajectory, the more fascinating the question becomes. Could this path point toward a specific stellar nursery or region where the object was originally formed? But the journey isn't always a perfectly straight line. As an interstellar object enters a planetary system, the gravity of massive planets can alter its trajectory. In our own solar system, Jupiter, Saturn, Uranus, and Neptune are powerful enough to dramatically redirect smaller bodies. These gravitational assists can leave subtle changes in an object's orbital path, almost like fingerprints. By studying those changes, astronomers can distinguish between an object's original interstellar trajectory and the path it followed after encountering the planets. And this is where the investigation takes an even more important turn. Knowing where an object came from is only half the mystery. The real question is what it is made of. A small fragment traveling between stars can preserve material from the planetary system that created it. Its surface, minerals, ice, dust, and trapped gases may contain a chemical record of its birthplace. Astronomers can analyze the light reflected or emitted by these objects and search for specific spectral signatures. Different molecules and minerals interact with light in distinctive ways, allowing researchers to build a chemical fingerprint of the material. If one interstellar object contains unusually high levels of certain ices, metals, or organic compounds, while another shows a completely different composition, that difference could reveal how planetary systems evolve under different conditions. In a sense, we don't need to travel to another star to begin studying its planets. Sometimes, another star system sends a fragment to us. And as more interstellar objects are discovered, astronomers can begin comparing these cosmic travelers, tracing their trajectories backward and decoding their chemistry forward. The ultimate goal isn't simply to identify where these objects crossed the galaxy. It's to reconstruct the environments that created them, and discover how different, or surprisingly similar, other planetary systems may be compared with our own. Because every interstellar visitor carries two stories. One is written into its trajectory, pointing toward the stars it may have passed through. The other is locked inside its material, waiting for us to decode it. And together, those two clues could allow humanity to study distant planetary systems without ever leaving the solar system. But tracing an interstellar object back toward its possible birthplace is only the beginning. The next challenge is far more intimate. We need to determine what is actually inside it. Every planet, asteroid, comet, and fragment carries the chemical conditions of the environment where it formed. Temperature, radiation, pressure, and the composition of the original disk around a star can all influence the materials that eventually become solid worlds. An interstellar object is therefore more than a traveler. It can be a geological time capsule. When these objects pass through our solar system, telescopes can study the light coming from their surfaces and surrounding clouds of gas and dust. Spectroscopy allows astronomers to separate that light into its component wavelengths and search for signatures associated with molecules, minerals, and different types of ice. Water, carbon-bearing compounds, silicates, and other materials can leave distinctive patterns in the spectrum. And those patterns matter because the chemistry of another planetary system may not match the chemistry we see around the Sun. For decades, scientists have studied our solar system as if it were a blueprint for understanding planets everywhere. But interstellar objects offer something fundamentally different. They give us a chance to test that assumption. Imagine discovering two objects arriving from completely different stellar neighborhoods. Their trajectories reveal separate origins, but their chemical fingerprints show striking similarities. That could suggest that certain planetary building processes are common throughout the galaxy. But if their compositions are dramatically different, the implications could be even more interesting. It could mean that the conditions surrounding different stars produce planetary materials in radically different ways. And there is another clue hidden in their journey. The longer an object spends exposed to interstellar radiation, cosmic rays, and extreme temperatures, the more its surface can be altered. By comparing surface material with deeper material released through activity, astronomers may eventually distinguish between the chemistry of the object's original birthplace and the changes caused by millions or billions of years in interstellar space. This turns every observation into a kind of forensic investigation. Its orbit tells us where to look. Its gravitational encounters tell us how its path changed. Its spectrum tells us what it carries. And its physical behavior can reveal how that material responds to sunlight, heat, and radiation. Piece by piece, astronomers can reconstruct the history of an object that may have formed before our own solar system existed. But perhaps the most astonishing possibility is still ahead. If enough interstellar objects are detected, scientists could build a population-level map of material drifting between the stars. Instead of studying one mysterious visitor, we could compare dozens or even hundreds. Some might be rich in water ice. Others could contain unusual minerals. Some might be fragments of larger bodies shattered by violent collisions. Others could be ancient leftovers from planetary systems that evolved completely differently from ours. Over time, these differences could reveal something much larger than the history of a single object. They could reveal how common, or how unusual, our own solar system really is. Because the galaxy isn't sending us empty messengers. It is sending us fragments of other worlds. And every one of them carries a chemical fingerprint from a place humanity may never physically visit. But tracing an interstellar object back toward its possible birthplace is only the beginning. The next challenge is far more intimate. We need to determine what is actually inside it. Every planet, asteroid, comet, and fragment carries the chemical conditions of the environment where it formed. Temperature, radiation, pressure, and the composition of the original disk around a